Hello everyone, welcome to today's class. And today's class is all about work power energy. We already started this chapter in our previous lecture. We already continued up to work energy theorem, and today's class we will start with the conservative force field, or next we will learn about the conservation of energy. So let's start. So what is conservative force field? Mainly, conservative force field is a type of force field, or conservative force is a type of force for which work is state variable. That means it depends on the initial position and the final position of the object, but it doesn't depend on the path of the path that travels object that it does not depends on the path which object travels. Okay, so that means, as we know, work done W equals to F dot dr and integration of that. Okay, so that means it depends on dr. Okay, so that means it depends on the path. So but for the conservative force, work done depends on the initial and the final position only, not depends on the path. Okay, so that type of force field is called conservative force field. And for conservative force field, that is our that is out of scope of our discussion. Means the derivation is actually out of scope of our discussion, but it can be shown that for conservative force field, where work done is depends on the state or the position of the object, not depend on the path. So for that type of force field, force can be defined as the uh, gradient of the potential energy. Gradient is actually spatial variation of spatial variation. Okay, so gradient of potential energy, that means uh, this is du dx or du dy or du dz. So that means that is the variation of potential energy for change in unit length or unit distance along x. So that is actually defined by the gradient. Gradient is actually a spatial variance, anything derivative with respect to space, that means x, y or z, actually termed as the gradient. Okay, so that is all about the gradient. So now if our force have three components along x, along y and along z, so fx can be shown as the gradient of, okay, that is with the negative sign. This negative sign is due to the conservation of energy. This negative sign actually due to the conservation of energy. And again I am saying that this derivation is out of our scope of discussion. So for fx, that can be defined as minus del u del x. Here this del is actually partial derivative. This is simple derivation or the differentiation, but this is called partial derivative. Partial derivative is such kind of differentiation where uh, mainly x, y, z, these things, these three things can connect each other. That means x can be a function of y, or can be function of z. The reason is reason completely depends on the path of the object, in which path it is moving, that completely depends on that. Okay, so it may happen if object got some amount of displacement in the y direction, it also have some amount of displacement in x direction. So for that case, x is a function of y. Okay, so this is a fact where x, y, z can be function of each other, but for that case we use partial derivative, and partial derivative actually shows deviation or a variation of anything with respect to a particular variable. That means if we are, when we are using del u del x, that means we are actually finding the variation of u with respect to x, keeping y and z constant. Okay, so if three of the term, which three terms are related to each other, and three of the terms are itself changing. So that is very difficult to understand the variation of u with respect to x, y, z as a whole. So that's why we actually wants to find out the variation of u with respect to x, u with respect to y, and u with respect to z. That means if x changes, how that u changes, keeping y and z fixed, because we just want to know about the dependency of x on u. Okay, so that's why we use this partial derivative. Partial derivative, again I am mentioning that during partial differentiation, if we are using part du dx, that means we are actually finding the partial derivative of u with respect to x, then for that case y and z is constant. Okay, so but that is not the fact for the normal differentiation, where if x and y and x and z, y and z, those have some kind of relationship, then del u del x, in finding du dx we can have some terms dy dx or dz dx. That kind of term can be there in finding du dx. Okay, so that's why we use always del u del x. So this thing is quite mathematical, and I don't think this is important for you people. So just for that timing, just understand what is del and what is d. For d, it can be u, actually u can be function of x, y, z, and x can also vary with y and z. So for that timing, x can be function of y and z also. So for by using normal differentiation, if you differentiate u with respect to x, you can see there will be some term called dy dx or dz dx. That means variation of y with respect to x and variation of z with respect to x. These terms can come into the calculation. So to avoid this, we use the partial differentiation, where we just want to see the variation of some parameter with respect to some variable, keeping the rest of the variables constant. Okay, that's why we use that. So this is fx is minus of del u del x, just similar to this equation. Fi is your minus del u del y, and fz is your minus del u del z. Okay, so that is our total expression for the force when the force field is a conservative force field. Okay, now as I already mentioned, the for the conservative force field, work done is a state variable or state function. That means it depends on the state, initial and the final state. Now if you find the work done on a closed path, that means you have started from A, then go to B, and then again come back to A. So the work done on this whole process will be 0 under the conservative force field. Okay, so you can understand, that means the friction is not a conservative force field, conservative force, because when you travel from A to B, you have to do against the friction. Again, when you are returning back from B to A, again you have to do some work against the friction. So that means there will be a total work done against the friction. Okay, so that is not a conservative force field. Okay, now why this force field is called conservative? Because the conservation of energy holds here. Okay, so let's start with the basic equation of the work done, that is force multiplied by the displacement, or in brief, or it can be written as a force dot product with the dx, that the displacement, f dot dx. So the force can be defined as mass into acceleration, so m into a dot dx. Okay, now a is our dv dt, that is the rate of change of velocity. Okay, so m into dv dt dot dx. Now m dv dt dot dx, now we can divide here with dt and multiplied with the dt. Okay, so that can be divided with the dt and can multiplied by the dt. So it will, if you just cancel each other, you cancel that dt, you will get this term again. Now from this term, this dx dt, dx is displacement divided by time, that is our velocity. So m into dv dt dv dt was already there, and dx dt is your v dot v multiplied by the dt. Again you can cancel this dt with this dt. So your final expression will be m v dot dv. Okay, now as we know, so change in velocity, now we are considering the total thing that the force is actually acted in the direction of the motion of the object. That means it is producing an acceleration in the object. That's why the velocity changes from u to v. That means there was an acceleration. Now that means if the object has some kind of acceleration, so in simple case the change in velocity will occur in the direction of the velocity itself. Okay, so that means, or if the object gets some retardation, that means the change in velocity will be in the direction opposite to the direction of the velocity, original velocity. Okay, so is I think it is clear now. Now take an example, an object is moving towards this direction. Okay, now with a velocity of 5 meter per second. Now if you want to get some kind of acceleration, you have to put a force in the same direction. Let you have applied a force of 5 Newton in the same direction of the motion of the object. So after that the object gets the velocity and its velocity has changed, it becomes 6 meter per second. Okay, so the change in velocity also occurs in the same direction of the motion because it got some acceleration. Okay, so that's why I am saying that this dv and v is in the same direction. Okay, so since both are in the same direction, so we can write v dot dv as mv dv cos 0 degree. So we know about a dot b is ab cos theta, so that will be v dv cos 0 degree, and v cos 0 degree is our 1. So simply vm v dv. Okay, now since our velocity has changed from u to v, so total work done, this is the elementary work done due to the displacement of dx. So then total work done w, we can find that by integrating this dw, and integration will be done over the velocity range from u to v. Okay, since the velocity has changed from u to v, so just m is constant, take this out of the integration of v dv starting from u to v. This is called limit. Okay, so there is an equation for this kind of integration. Integration of x to the power n dx is our x to the power n plus 1 by n plus 1. Already I have mentioned in our previous lecture. So here that is v to the power 1. Okay, so result of this integration will be v to the power 1 plus 1, that means v square, divided by 1 plus 1, that is 2. That means m v square by 2. Okay, just take this 2 out, so you will get m by 2 of v square. Now you have to put the limit there, so just put the upper limit first, you will get v square, then put a minus sign in between, and then put the lower limit here, so you will get minus u square. Okay, so that will be our total work done, that is half of mv square minus half of mv square minus half of mu square. That is the change in kinetic energy, and it is also the work energy theorem. Okay, now again work done dw is f dx, and f can be written now maybe minus du dx I cap. Why minus du dx I cap? That force is in the direction of the motion of the object, so that because the force is actually producing an acceleration, so it is in the direction of the motion of the object. So now the object has displaced in the x direction, that is dx, so that is in the x direction, so that means force must be applied in the same direction, means it will be in the x direction. So the force is from the previous expression, it is minus du dx, and force is a vector and the direction is in the x direction. That means value is your minus du dx and direction is I cap. okay, and dx vector can be written as dx into I cap. Okay, so dot product between two things I dot I will give you 1. So it will be your minus du dx into dx, dx will cancel, you will get minus du. Okay, so net work done will be W of integration u1 to u2, because let u1 is your initial potential energy. That means you got some amount of potential energy, and that was u1, and after application of force the potential energy has been changed and it becomes u2. Okay, so that means integration will be performed from u1 to u2. So just take this minus out, integration of du will give you u, starting from u1 to u2, just put upper limit here, so you will get minus sign, just take the minus out here. Okay, now put this u2 first, u2 minus, put the lower limit, that is u1. Okay, now just take this minus sign in, no, that will minus u1 will be plus u1 and plus u2 will be minus u2, so that will be u1 minus u2. Now work done must be same, because we are talking about the same phenomena. So we can equate this to equation, and so we can just take this u2 from here to here and take this half of minus half of mu square here to here, will get u1 plus half of mu square equals to half of mu square plus u2. This is the potential energy, this is the kinetic energy, this is the kinetic energy, this is the potential energy. That means initial total mechanical energy must be equal to the total energy after the application of force. So this is the conservation of one energy, and it holds good for the conservative force field. Okay, now we will talk about some cases and we will see how conservation energy holds there. Okay, so first of all, there is an object, first case, that is the first problem where we are dealing with an object that is falling freely under the gravity. Okay, so acceleration due to gravity is working towards down, and that value is g. Now let's start. That is a free fall, that is a free fall. So that means initially the object was at A, then after some time t it reaches to B, and after another some moment it reaches to C. So when it was at A, it starts from rest, that means the velocity was u. When it was at B, the velocity is v1, and when it was at C, the velocity is v2. Now the distance between A to B, that is x, that means the object has traveled a distance x to reach from A to B. Okay, and the total height of A is actually h, so that means height of B will be h minus x. This one is x, this total one is h, so B is at a height h minus x from the ground. Okay, so let's start. At A, that kinetic energy will be half of m of 0 square, since velocity is 0, so that was 0, and the potential energy will be mgh, since height is h. Okay, so that means total energy at A, that is denoted by E suffix A, Ek plus Ep. Ek is your kinetic energy and Ep is your potential energy. So 0 plus mgh, it is mgh. Now fine. Now at point B, now to start with the calculation of total energy, we have to first find the velocity of v1. What is the velocity of the object at the point B? So now let's take the motion of the object starting from A to B. The motion is started from A and ended at B. That is our assumption. Started at A, that means the initial velocity of the object was u, and ended at B, that means the final velocity is v1. Now by using this formula, v square equals to u square plus 2i is our final velocity is v1, that means v1 square equals to initial velocity was 0 square plus displacement was x, that means plus 2 into g into x. Why it is A? Why we put g in A? Because the object is falling freely, that means the acceleration is due to the gravity. So we have to put the acceleration of the object as the acceleration due to gravity. Okay, so v1 square is our 2gx. Now find out the kinetic energy. The ek is half of m1 v1 square. Put the v1 square here, half of m2gx. That since v1 square is 2gx. Now this 2 cancels mgx. Okay. Now potential energy. Potential energy is m into g into height. Height is your h minus x. Now put h minus x here. So you will get mgh minus mgx. Now total energy will be EP plus EK, potential energy plus kinetic energy. That is mgh is your kinetic energy, potential energy is mgh minus mgx, and plus mgx is your kinetic energy. So mgx and minus mgx will cancel, and your final total energy will be mgh. So total energy at B is exactly equal to the total energy at A. Okay. Now what about the point C? Now at point C we have to first find out the velocity at point C. So for that case we will consider the motion starting from A and end at C. So object started from A and ended at C. That means initial velocity is 0 and final velocity is v, and the displacement is total h. So for that case, if we use this formula v square equals to u square plus 2as, v square equals to u square plus 2as, will get final is v square equals to initial was 0 square plus 2 small g into h. Why it is h? Because displacement is h. A to C, there is total displacement was h. Okay. Now your v square is 2gh. That means, so kinetic energy ek is your half of mv square, and that is half of m multiplied by 2gh is your mgh, because you have to cancel this 2 with this 2. Okay. Now the potential energy, since the object is on the ground, that means the height from the ground is 0. So potential energy will be mg into 0, that is 0. So total energy E at C, that is ek plus ep, you will get that is mg. So that means total energy at A, total energy at B, total energy at C, all these three has the same value mgh, that holds the conservation of energy. Okay. So we prove that for a object that is falling freely under the gravity, conservation of energy holds. Okay. So you have to keep one thing in your mind, we didn't consider the resistance offered by the air during the falling, and again one thing, that is the upthrust due to the air. Okay. So we just assume that is an ideal condition where those forces is not present, that means presence of air is not considered here. So for that case, that means one force is present, that is only the gravitational force, no other force field was there. So that means for only gravitational force field, conservation of energy holds. That means gravitational force field is the conservative force field. Okay. Now next thing is that, next thing we just want to prove is the conservation of energy for an object that is moving on an inclined plane. Okay. This is an inclined plane of length capital L that has an angle of inclination of theta. The total height at the extreme end of the inclined plane is from the ground is h, capital H. Okay. So the end is at an height capital H from the ground. Now again we consider the three position of the object. Initially the object was at C, and just we have to keep in mind this object is coming down due to gravity only. That means there is no other force of application on it. So no force, other type of force is applied on the object. So this is coming due to its own weight. So this, that we have to consider three position. Initially it was at C, where the velocity of the object was 0. Then after some time it reaches to B, and finally it comes to A. Okay. So this is the whole idea. Now B to C, this distance is L. At position B, the height of the object from the ground is small h, and as you can see, we just assumed that the vertical displacement from B to C, that means this height from vertical displacement from C to B is x. So that means this small h is capital H minus x. Okay. Now start with the point C. The velocity is 0, that means kinetic energy is 0. Potential energy mg is capital H, since height is capital H. So total energy is mgh. Okay. Now at point B, the velocity of the object is let v1. Okay. So now we have to consider for the motion from C to B. Now C, that means starting point is C, that means initial velocity was 0. Final point is B, that means the velocity is v1. So for the motion C to B, acceleration on an inclined plane is g sin theta. Okay, and it can be shown, and I think it was shown in our discussion on the laws of motion. Or if you don't check that out, that means if you don't go through the note of laws of motion, or if you don't watch the lecture on laws of motion, then I just show this here. So this is mg. Okay, now mg can be divided into 3 components. This angle is your theta, so this angle is theta, that means this angle is theta. So it is a well known problem. So this angle is theta, so mg is here downward. So that means the mg can be divided into 2 components. One is mg cos theta, that will be here, and one will be mg sin theta here. Now you can see this mg sin theta will pull the object along this inclined plane. So there will be a net downward force mg sin theta along the inclined plane. So total force F equals to mg sin theta. F is your m into a equals to mg sin theta, and this mm will cancel and a will be your g sin theta. Okay, so that means acceleration of any object on an inclined plane is g sin theta. Now just put here v1 square equals to 0 square plus 2 in the position of a, you put g sin theta, and your displacement s is L. Okay, is L. So v1 square equals to 2g into L sin theta. Now for this triangle, find the L sin theta. For this triangle, find the sin theta. So you will get for this triangle, that means this smaller triangle, you will get the sin theta as height by hypotenuse. Your height is x and hypotenuse is L, that means x by L. So L sin theta is your x. Okay, now just put L sin theta x, so 2gx, your v1 square is 2gx. Now find the kinetic energy, ek equals to half of mv1 square, put value the v1 square here, we will get mgx. Find the potential energy, that is mg small h. H small h is the height of that point V. So capital H minus small x, just put here, total energy will be that potential energy, kinetic energy plus the potential energy, you will get, that is mgh. So mg capital H here, mg capital H, that means total energy at B and total energy at C both are same. Okay, now for the point at A, that means at the ground, the velocity is v. So for the motion from C to A, that means at C, that means initial velocity was c 0, and at A, that means the final velocity is v. So if you use this equation, v square equals to u square plus 2as, you will get v square equals to 0 square plus 2 a, acceleration is 2g g sin theta into capital L. L is total displacement starting from A to C to A, that is the total length of your inclined plane. Okay, now just L sin theta. Now for this whole triangle, find out the sin theta. It will be height, that is h, by hypotenuse L. So L sin theta will be capital H. Okay, just put the value of L sin theta capital H here. Now total kinetic energy will be half of mv square, that means mgh. potential energy is 0 since the object is on the ground, so net energy will be mgh. So again we proved the conservation of energy for an object that is coming down over inclined plane. Okay, so that is the end of our discussion, and I think that is the end of this chapter also, since we already covered the collision part in our laws of motion classes. So that's all. Thank you.